All right, hi everybody. Okay, so real quick at the beginning of class, I'll talk a little bit about midterm distribution. Midterm is a little bit more challenging, I think, than the average midterm, which is better to have that happen, average first midterm, which is good to have it on the first midterm rather than the second, because the first one's worth only 15 to 20 grade, and it happens earlier. So students who were caught flat-footed this time have plenty of time still to catch up and to change their study habits or whatever, find the right office hours, whatever it takes to figure out what they need to do before the next midterm. What happens sometimes is I'll make the first midterm and I'll just calibrate it wrong, make it too easy. Everybody, the grades will get crushed up toward the high end, and then people stop coming to class and studying and whatnot, and then the second midterm comes around and they get hammered, and it's pretty late in the semester. That's 25 senior grade, the second midterm. It's pretty late in the semester to recover. So it's better to have a little kick in the slats now than second midterm. So I'll show the distribution of grades. And today we're going to do rotary motion. We're going to talk torque. Woohoo! That's right. So there's two topics. And the GSIs have it's not really a joke. They have sort of a saying that in this class, so some students don't learn either of these topics, but students seem to either learn fluids or they learn torque. Like some students find torque more natural, some find fluids more natural. It's that rare student who really feels comfortable with all the material. But this is one of the most vexing topics in this class for a lot of students. Is torque. We'll do that today, and we'll be doing it this week, and it'll continue for the next few weeks to be an important aspect of all the things we're learning. But we're going to introduce it today. Yes, and we'll talk about other angular aspects of rotary motion. All right, but real quick, I'll show you this. I don't know, have you seen the distribution of the grades yet? Can I get the Elmo up on the? There we go. Have you guys seen that yet? No, okay, so here's the distribution of grades. Lots of good grades in here. Lots of people did really well. There's even scores just crammed up at the high end. The mean score was 66. Well, there's lots of different averages here. Like the mode was 75, if you care. The median was probably a little higher or lower than 60, I'm not even sure. So it's pretty Gaussian distributed. So it's a pretty reasonable distribution of grades. If I'm going to send out, so at this time in the semester, I send out midterm grades. They don't affect you in any way, except that it lets you know essentially what I'll do is if you got like 50 or below on the exam, you'll get an automatic note from me saying, oh, watch out, you should put a little more time in for the end of the semester. If you want to talk to me about it, come to my office hours. We can set up office hours actually following my usual Wednesday morning office hours when I come and talk about your study habits or what's giving you trouble in the class or whatever. And even if you got 98% on the exam and are disappointed with your score, come and talk to me. Like, do it. This is the time of the semester to figure out what you need to do to get the level of understanding you want. I think the way you grade these exams is pretty fair. You'll get them back in your. We work pretty hard to grade them fairly. You'll get them back in your sessions. Has anyone gotten your test back? Oh, some of you already have. So the way it works, you'll get it back in your session this week. You'll be asked to put away your pencils and pens, right, and your erasers and all those things, and then they'll pass out the exams. Your GSI will. You'll look over the exam. Most important thing. Make sure the points that you got for each problem add up to the total amount of points you got in the exam. The most common legitimate claim of a problem with grading is that somebody made some sleep-deprived GSI accidentally added 10 and 10 and got 15. So make sure you got all the points you were owed on the front of the exam, and look over other things too. If you think something was graded improperly, but you'll be asked to justify, right, concisely in writing on a separate sheet of paper. Your GSI in section will have you hand back your exam if you think there's a problem with the grading. You'll justify, okay, here's what I think is wrong with the grading, and then we'll go back to the GSI who actually graded that problem, who's not your GSI. We do that intentionally, so your GSIs aren't grading problems. And be aware, your grade can go down if you do this. Like if they get it back and say, oh wow, now that I scrutinize it more carefully, I see that there's all this mistake over here, and I gave them the benefit of the doubt last time, but now I'm looking more carefully. So it does happen sometimes when grades go down. So don't just turn it back in just in the hopes you'll keep raising your score when you turn it back in. Make sure you have a specific, legitimate concern about the way the grading was done. And once you walk out of the room with your exam, we can't take it. There's no regrades, right? You have to do it. You can't leave the building with the exam and bring it back. Okay, good. So I'm pleased with the distribution of grades. It's a little bit lower mean than I tend to like, but not so low. That's a pretty good distribution of grades. And again, we're early in the semester. Now's the time to change course if you're not doing this well as you want. Yeah. Oh, that graph will be it'll probably be up in the course room and stuff like that. I can put it online. You'll have access to that. Yeah. And you'll have your own scores back soon if you haven't got them already, which is probably even more significant to you. So all right. Rotary motion. So I did a couple quick demos at the end of the last lecture. Many of you weren't here. I'll just do it real quick. I'll remind you what you saw if you saw it, and I'll show you what you would have seen had you come. The idea is that I've got an object over here that can rotate. Let me get this out of the way, much as I love it. I've got an object over here that can rotate. It's just a wheel on a horizontal wheel, and I've got string wrapped around the axle of it, and I've got it going over here to an ideal pulley, up to another ideal pulley. We've got weights hanging on the end. They're all hanging another weight on here. Oh, and there it goes. So there is some sort of momentum, some sort of angular momentum, some moment of inertia that keeps this guy from just being able to spin arbitrarily fast right off the bat. So we're exerting some force on it to tension in the string, right? But notice that this thing's not, its center of mass isn't moving, right? So it's not like there's a card down here that has to be accelerated along in order for that guy to be accelerated downward. Like most of the problems we've seen so far, we've got a rope between two objects, right? Instead, what's going on is that something has to be spun up. It's being angularly accelerated. And there's some resistance to this. In the same way that there's resistance to linear acceleration, right? F equals ma, the bigger your m, the bigger your mass, the less you will accelerate in response to the same force. There's an analogous idea for angular motion. In other words, there's a moment of inertia which acts like the mass. The bigger your moment of inertia, the harder it is to accelerate you in the angular sense, right? So we're going to work all that out right now. This is just one example of that. And there's going to be some sort of surprising consequences of this. Let's see. For example, here, let's do this real quick. Suppose we've got a ramp. We've got a couple objects that are round, a couple wheels, and they're equal mass. So I've got them on a scale right here. See that? So these are just round wheels, right? And I've got them, and they're the same mass. And we've already seen that the mass doesn't affect. We've calculated a few times now how fast it's accelerated, how great the acceleration is when we put a mass on an incline. Even with is that true with friction? Well, let's see. Certainly without friction. Let's keep it simple. Suppose there is no friction. If I put a mass on this thing and let it slide down the ramp, right? In that case, it's just a function. The acceleration of the object down the ramp is just a function of the angle, right? Because remember, we work out Newton's second law. We do it with the normal component. We do it with the component down the ramp. And that 20 times in class, and you do it many times on your own. And you find that it's just the component of the force of gravity that goes along the ramp that matters. So the motion along, we call this the x direction, down the x direction, right? The bigger the angle, the faster the greater the acceleration is. If you have a vertical ramp, right, with no friction, even if there is friction in that case, what you wind up with is essentially the acceleration is the same as gravity, it's g. If you have a flat ramp that's horizontal, then you get no acceleration at all because there's no component of gravity along the ramp. And then intermediate levels, well, the bigger the angle is, so it's what is it, sine or cosine of theta? This is theta. I guess it starts off at 0, so it must be sine of theta. So it's g sine theta is your acceleration down the ramp. And it doesn't matter what your mass is. But just to be pedantic, I'm showing you these two wheels have equal mass. So mass isn't really, that's not the issue. So I'm going to roll these guys down the ramp. You see this up here? Oh yeah, great. I'm going to roll these two down the ramp. And let's see if one beats the other. Sure enough, one is, oops, almost got away from me. As always, one is a little faster than the other, right? Now how can that be? They must have different accelerations. Another question is, are their accelerations constant? We know the answer for an object sliding down a ramp with no friction. In fact, even with friction, we know. It is an example of constant acceleration. I'll tell you right now, this is too. It's just that the acceleration values for these two objects is different, right? And we're going to be able to calculate that in a couple different ways. But we're going to have to think in terms of angular acceleration. I'll cut to the chase a little and tell you what's going to happen, and then we'll go through it formally and see how it works. But these two wheels have the same mass, right? Their total mass is the same, but the distribution of mass is different, right? This guy has most of its, or a greater density, so much of its mass, near the middle of the wheel, the axis of symmetry of the wheel, right to the middle. And you can see that because it's a shiny little piece of brass here, right? So it's got a brass core, and it's got wood around the outside. Now this one has wood in the middle and brass on the outside. Brass is denser than wood, more mass per unit volume than wood. Same total mass, but different distribution. This has more mass away from the center. So which one, let's see which one goes faster. So the one on my side has more mass toward the outside, and the one on your side got more mass on the inside. So which one's going to be faster? What do you think? More mass on the outside faster, or more mass on the inside faster? Inside. All right, let's see if that's true. I think that's right. Yeah, it's really true. That's right. So more mass on the inside goes faster. And there's going to be two ways we can think about it. Just like with linear acceleration, when F equals ma, we can solve problems that way. But then if we're asked the question, suppose the question is, well, who's going to be moving faster at the bottom of the ramp? Faster. That's a question about speed. If I'm given a problem where I'm given the initial conditions, and there's not going to be any dissipative forces in the problem, and the thing I'm asked for is not how long it takes, but how fast something's moving at the end. What am I going to do? Am I going to use constant? You can use Newton's second law, but what else can you use to solve that problem? Conservation of energy. That's right. Conservation laws are convenient that way. It'll turn out that'll be true in this case. We can use conservation of energy to solve that as well. But we have to account for all the energies, not just the linear kinetic energy. We have to worry about the rotational kinetic energy. But we'll get there. So to start all this off, let's just start making a big table of things we know from the linear case, and then write the analogous quantities for the angular case. And I'm going to use this board because I'm going to find 2 boards worth of material. So here's the right here. So this will be linear stuff you already know, and this will be angular. Or some of you know this as well, but it's stuff we haven't really introduced formally in class yet. All right. So the first thing is just like in the beginning of the class. The first thing on the first day of class, you talk about position, where something is. Well, let's just keep it one-dimensional. We'll say x. All right. All right. So what's the analog of x? Well, the analog over here is going to be theta, and we can call it different things, but we'll tend to call it theta. Just like we can call this y if you want. So theta is your angular position. So let's think about how to relate x and theta. Maybe I'll do that on this board over here. This will be my charts of my linear and angular, and then I'll use other boards for describing the various relationships we put out there. So if you've got some wheel, just like we have a problem here with rolling wheels, right? You have a wheel that's rolling along the ground without slipping. So here's your wheel, right? Maybe I'll draw it in bigger. Just make sure everybody can see it. So I've got some big wheel, right? It's a little egg-shaped, but you get the idea. Here's the center of the wheel. It's got some radius r. Okay, that's an important length in our problem. It's going to provide a length scale for us. And it's rolling along the ground. Now, I know in the example I just gave it was rolling down a ramp, but just for right now, it's on the ground. The same equation either way. But the idea is that it's rolling without slipping. When those guys rolled down that ramp, right, they weren't sliding. Just like that cartwheel example we talked about before. When you have something that's rolling along the ground, the part that's touching the ground is not sliding. Right? It's holding still with respect to the ground. So in that case, if we ask how far does the center of mass go in the x direction, let's call this the x direction. So my x-axis is going along to your right, right? And I'm saying, where's the center of mass? How far does it go when I roll the wheel through some angle theta? Well, if it starts off like this, okay, and if I drew this properly, a line that goes straight down from the center of the wheel ought to be touching the ground. So make this wheel actually round. Touches the ground. That's a little less potato shaped, a little more like a real wheel. There we go. So it should be touching the ground just at this one point right here, the perfect circle. This is the horizontal line. A line straight down from the center reaches that point, that tangent point, right? And then if we ask, well, suppose I roll the wheel over some angle theta. So I roll it along, right? So now the center of mass is over here. I redraw my wheel. It's over here someplace, right? And it's moved over this far. And then it's gone through some angle, right? So I've got some new wheel location, right? So it's undergone some change of angle, which we decided to call theta. How do I relate theta to how far the center of mass went? Well, that's also how far the point of location, right, the tangent point moved along the ground. You know, the wheel used to be here, now it's over here. Well, that distance, if I drew this properly, that distance should be the same as that arc length, so I didn't draw this properly. I made my theta too big. So let's make theta a little smaller. That's still too big. My picture's imperfect. But the idea is that this arc length along here should be the same as that distance. So this distance, we can say, oh yeah, that's my distance x along this x-axis. Let's say that this is x equals 0 at this moment right here, at this position right here. Then this is some new location for the center of mass. The wheel moved over by some distance x and underwent some change to theta. Okay, you get the idea. Well, what's the relationship? Well, first of all, what units am I going to express theta in? So I would use radians to make my equation simple. I can use degrees if I want, but if I use degrees, I have to have an extra factor in there to convert it into radians. There's pi radians for how many degrees? 180. Yeah, that's right. There's 2 pi and 360, so there's pi and 180, 90 and pi over 2, whatever you want to do. But let's just put everything in radians to make our life simple. So x then equals, well, it's proportional to theta. The bigger theta is, the bigger x is going to be, right? If theta equals 0, if I rotate it at all, then the center of mass doesn't move at all. Makes sense. But what is the proportionality constant going to be right here? R or 1 over r? So the bigger r is, does that result in a bigger x for the same theta? If I make a bigger r? I think so. If I have a really big wheel, if I just turn it a little bit, it moves a lot further. In fact, there was an advertisement I was on TV for a new wheel. They were selling some mag wheels or whatever on TV. To my show I was watching. But anyway, they said, oh, you'll save gas with these bigger wheels, the bigger radius, because for the same, if you just turn the wheel the same, rotation distance, you'll actually go further along the ground, which is true. But it'll probably take more gas to do that than it would, like the guy didn't take his physics seriously when he told us this is bad advertising. Anyway, they have better rules in place now. Anyway, so for advertising, so yeah, that wasn't true. But the basic idea that if you have a bigger wheel and you rotate the same distance theta, or same angular distance theta, yeah, I get you bigger x. So it better be r right here, not 1 over r. And what's more, the units make sense now. So remember, the way the units work with angles is a little bit weird. You have to remember to put in theta in units of radians for this equation to make sense. You put in degrees, you need to multiply by, again, that factor we said a minute ago, right? Pi over 180. But if this is in radians, then, and this is meters, well, then this equation is correct. So that means that you have meters equals meters times radians. That seems weird. So the way we think about it is that we always express our angles in terms of radians, but we don't explicitly refer to those radians in an equation. We think of this as a unitless quantity in the context of an equation like this to get our units right. And that's sort of unfortunate because it means if we have thetas floating around, we don't get to use unit analysis to see if they're correct or not. It also means that students will get mixed up. Like, well, wait a minute, this thing is they got to divide by some other angle to get rid of the radius. No, that's not the way it works. We don't include the units here. We think of it. We think of it as a unitless quantity. And one way to think about that too is that theta often appears inside trigonometric identities, like sine of theta or cosine of theta. Well, you can't have units inside the argument of cosine or sine. right? So that's another tip-off. That in terms of equations, we're not going to include any stated unit for an angle like theta. But we'll just have to remember that there are many different conventions for expressing angles. If we want these equations to make sense, just got to make sure it's convenient. All right, that was a very long-winded description. So suppose we know about other things, like the velocity, right? Maybe the velocity in the x direction, or the acceleration in the x direction. What's the analog? Okay, I'll put them, so the reason I do this a little to the left, I give myself a little room. I'm going to put sort of typical equations. You'll see over here to relate these things. So this is a typical expression. X equals some typical length scale using the radius of a wheel, right? Not always. Times theta, right? And we can also talk about the arc length of something. Say, well, that's also r times theta. The arc length, by that I mean the distance along the circumference of the wheel that corresponds to a change in theta. Again, that's just r times theta. That'll give you the arc length. In other words, if we have a tape measure along the wheel and say, well, if the wheel rolls, right? If the wheel starts off right here and it rolls along some distance. If we have a tape measure along the edge of the wheel from where it was initially touching the ground to where it is now, that distance, if we flatten it out, is exactly the distance along the ground the wheel moves. Right? Makes sense, but just so it's clear what I'm talking about. So great, we have that. What about these expressions? Well, we know it. This is just dx dt, right? So that means that if we just take the derivative of this with respect to time, we'll get what we call the angular velocity. Omega was the symbol used for that. Well, that's just going to be d theta dt, all right? First derivative of theta with respect to time, and that's going to have the same relationship to v as theta does to x, right? We're going to have omega equals r times omega. Oh, sorry. We're going to have omega on both sides there. Better be omega over here, the angular quantity on the right, if I have my r multiplying it, to get something with units of meters per second, right? So v sub x, the velocity is meters per second, that's meters. So what are the units of omega? Well, we'll say that they're inverse seconds. Once again, we have to think of it in terms of, it's got to be radians. You only have degrees per second, radians per second. But we don't include the radians when we figure out whether the units are the same on both sides of the equation. Looks good. Same thing here. dvx dt. Oh yeah, we can write that another way. Second derivative of x with respect to time, right? Same old, same old. And then over here, we'll call it alpha. So alpha will be our angular acceleration, right? The omega dt, otherwise known as second derivative of theta with respect to time. Great. And again, we'll get acceleration a equals r alpha, right? Alpha's got units of 1 over second squared. And again, express it in radians, right? Make sure you got radians. So one thing I should mention too is I guess I should put my a sub x here to be clear. So I mean it's the x component of a. I can also put another subscript here, which is that in the context of this problem, what exact acceleration are we talking about? Different parts of the wheel are accelerating in different ways. I'm talking about the x component of the acceleration of the center of mass of the wheel. Right? That's what I mean by a sub x. That's really important. It's going to turn out that in almost every case we care about, not always, I guess, you might solve a problem in a different way, but it's almost always going to be the case that when we're relating angular quantities to linear type quantities, or kinematics, or motion, we're going to care about the center of mass. That's going to be the special point of the object that enters into Newton's second law, that enters into the equations we're going to use. So that's usually the relationship we're looking at. The relationship between the angle of some rigid object that's rotating and translating and moving, right? And the motion of its center mass. Right? All right, great. So that's just describing the positions and motions of things. That's just kinematics, right? Study of motion. We haven't gotten yet to the physics stuff, but there's analogs to all that as well. Let's see, what's the natural one to do next? Let's do mass next. So I've already talked about that a little bit in the context of this wheel, right? Where I said, well, and also in the context of these wheels going down that ramp, we said, well, they have the same mass, but in terms of how quickly it was able to be accelerated in the angular direction, in angular sense, right? One wheel was more amenable to that than the other. One responded to the forces on it by spinning quickly, more quickly sooner. So what is that? What is the quantity that's analogous to mass that sort of dictates how fast the torque on something, which is we'll get to that in a minute, how fast the forces acting on it and where those forces act actually result in a change in the angular velocity of the object. Well, that's going to be the moment of inertia, which is written I for reasons I can't fathom. But so they made the letters probably. We already have M for mass. But anyway, I. So moment of inertia. All right. What is the moment of inertia? Well, one thing I'll tell you right now, we'll get into this in a bit, is that any given rigid object, like this piece of chalk, right, actually has many different moments of inertia associated with it. The moment of inertia depends on exactly how it's, well, I shouldn't say how it's rotating. I should say how it's rotating and where you choose to define your pivot points to be. So we're going to, in the way that we normally think about like any problem in physics, the first thing we do, we draw a little drawing, right? We draw our axes, we define an x-axis, a y-axis, right? All these kinds. Where's our origin, right? In the same way we can come up with those conventions for each problem. We also, with rotary motion problems, have a few more things we have to define. A few more conventions we have to state. One is, where's the pivot point? Where's the special point we're going to use to measure things like the moment of inertia and the torque and et cetera, right? Another is what we call the positive direction versus the negative direction of rotation. That'll be very important. So I'm just throwing that out there. You're going to hear a few things over and over through the lecture, and we'll solve problems with that, and you'll see what I'm talking about. But I just want to get in your radar screen before we actually see it at work in a problem. So what is the moment of inertia? Well, the moment of inertia is bigger when something has a, well, for one thing, it can be bigger with bigger mass, generally. Same distribution, we just turn the mass everywhere in an object, it'll get bigger. But it's also the case that if the mass is further away from the axis of rotation, or further away from the pivot point you're using to measure the moment of inertia, you get a bigger moment of inertia. If all the mass is concentrated right at the middle, then spinning the object around that middle isn't so hard. So it winds up involving both distance and position. So I'm going to put a sum here. It can also be written as an integral if your distribution is continuous. But let's say you've got n objects in some whatever it is, some system of particles. And you say, what's the moment of inertia? They're all rigidly connected to one another. Say, well, you sum over the mass of each of those little pieces, and you multiply by the distance, the radius of each of those things squared, and the distance as measured from the pivot point. So let's look at an example of this.